All right, your chemistry exam is just around the corner, and we are going to absolutely nail it. Welcome to your high-speed, no-fluff cram session on chemical reactions. We're going to turn any confusion into pure confidence in, like, the next 5 minutes. You ready? Let's jump right in.
Okay, right out of the gate, let's get those brains fired up. Think about this. You see changes all around you every single day. Water boiling for coffee, the gas flame on your stove. They seem kind of similar, right? But one of them is a totally different beast. One's just a temporary physical change, and the other, it's a permanent chemical one. So which one is which?
And here it is. A physical change, like boiling water, is totally temporary. You can get that water back, right? You're just changing the state of H2O, not the H2O itself. But a chemical change, like burning gas, that's permanent. You're creating brand new stuff. Carbon dioxide, water vapor, you can't unburn it. So the big takeaway? Burning gas is the chemical change. That is the fundamental difference.
So now that we've got the basics down, let's get into the patterns. Honestly, recognizing reaction types is like having the playbook for your exam. If you know the plays, you can't be surprised. We'll start with a couple of the most common ones you'll see.
First up, decomposition. The name kind of gives it away, right? Something is decomposing. You have one single, more complex thing, and it just breaks apart into multiple, simpler things. It's one thing becoming two or more separate things. Simple as that.
Here's a perfect example. You take some silver chloride, you let it sit in the sun, and boom, it decomposes. You start with just one compound, that's the AgCl, and it splits into two totally separate elements, solid silver and chlorine gas. See, one thing becomes two? That is a textbook decomposition reaction.
Okay, next up is the double displacement reaction. My favorite way to think about this is like two couples on a dance floor who suddenly decide to swap partners. You start with two compounds, and they just exchange their positive and negative ions to form two completely new compounds.
Let's see this dance in action with sodium sulfate and barium chloride. Look what happens. The sodium and the barium ions just trade places. Sodium ends up with chlorine, making good old table salt, and barium pairs up with the sulfate. Two totally new compounds, all from a simple swap.
Now, reactions aren't just about shuffling atoms around. They're also all about energy. Some reactions give off a ton of heat and get super hot, while others actually absorb heat and get chilly. Let's break down this absolutely crucial distinction.
It's really straightforward when you see it like this. Exothermic means heat out. Think exo for exit. It releases energy, so the temperature goes up. Endothermic means heat in. Think endo for enter. It absorbs energy from its surroundings, which makes the temperature drop. See? Exo for exit, endo for enter.
And you're definitely going to see some of these classic examples on the test. Mixing water with quicklime or carefully diluting an acid, yeah, those get hot. They're exothermic. But on the flip side, when water evaporates off your skin, it cools you down, right? That's because it's absorbing heat. That's endothermic. Just like when dry ice sublimates and makes everything cold.
All right, deep breath. This next skill is completely non-negotiable for your exam, balancing equations. It's kind of like a puzzle. You just have to make sure you have the exact same number of each type of atom on both sides of the arrow. Let's walk through one together.
We're going to tackle the famous thermite reaction. Right now, if you look at it, it's a mess. The atoms just don't add up. We've got two iron atoms on the left, but only one on the right, and two aluminums on the right, but only one on the left. We got to fix this.
Okay, let's do this step by step. First, we take inventory. We see we need more iron on the product side, so let's put a big 2 in front of the Fe. Great, iron's good, but now our aluminum is off. No worries, we'll just put a 2 in front of the Al on the other side, the reactant side. And now, the final check. 2 irons on the left, 2 on the right. Yep, 2 aluminums on the left, 2 on the right. Check. And the 3 oxygens were fine the whole time. Perfect, we are balanced.
Okay, let's level up to a slightly more advanced topic. Redox reactions. This whole game is about electrons moving around, and our job is to identify the key players, the oxidizing agent and the reducing agent.
First, let's talk about the oxidizing agent. Think of this guy as the electron thief. It's the one that takes electrons from another substance. And here's the part that can be a little tricky. Because it gains electrons, we say the oxidizing agent itself gets reduced. A great way to remember this is the mnemonic GR. Gaining electrons is reduction. So if you have an electron thief, you need an electron donor, right? That's the reducing agent. It gives its electrons away. And by losing those electrons, the reducing agent itself gets oxidized.
The mnemonic for this is LEO. Losing electrons is oxidation. So just remember the phrase, LEO. The lion says grr. It's cheesy, but trust me, it works every time.
Let's put Leo and Jur to work with a practice problem. Here we've got iron reacting with water vapor. One of these is giving away electrons and the other is taking them. Let's play detective and figure out who is who.
So here's how it all breaks down. The iron loses electrons to become part of that iron oxide compound. Losing electrons is oxidation, so iron got oxidized. And the water? Well, it gained those electrons to become hydrogen gas, so it got reduced. And here's the final piece of the puzzle. The thing that gets reduced, the water, is the oxidizing agent. And the thing that got oxidized, the iron, is the reducing agent. They always have the opposite role.
Wow, you've taken in a ton of information. So, what do you say? Let's put it to the test with a little pop quiz. Let's see what's stuck. Get ready.
First question for you. Imagine you're in the lab. You pour some sodium hydroxide into water, and the beaker starts to feel pretty warm. Then you take some regular table salt, sodium chloride, pour it into water, and the beaker gets cold. So, what is happening here?
If you said the sodium hydroxide process is exothermic and the salt dissolving is endothermic, you are 100% correct. The NaOH releases heat, it's exothermic. The NaCl absorbs heat from the water, making it feel cold, it's endothermic. Great job.
All right, question number 2. You run electricity through water, a process called electrolysis, and it splits into hydrogen and oxygen gas. What type of reaction is that? And for bonus points, what's the ratio of hydrogen to oxygen gas that you end up with?
And the answer is, it's a decomposition reaction. You're starting with one thing, water, and breaking it down into two simpler things. And that ratio? Well, the formula is H2O, so you get 2 parts hydrogen for every 1 part oxygen. The ratio is 2 to 1. Excellent work.
Okay, and for our final thought. When a silver spoon gets that ugly black tarnish, it's just a chemical reaction with sulfur in the air. Chemistry is happening all around us, all the time. What other invisible reactions are going on right now? Rusting forming on a car, a plant growing outside, or even the reaction powering the battery of whatever device you're watching this on. Always stay curious. You've got this. Now go ace that exam.